Concavity. All right. How many of you have heard the term concave before this class? What other subject has discussed it? Physics. What did you say? Some sciences. Physics is the one I've heard all day. Okay? So, what is it dealing with in physics? Mirrors and lenses and stuff like that. So concave is one kind. What's the other kind called? Convex. Okay? Somebody remembered also that concave was used in geometry class as well, right? Okay. In calculus, we don't have convex. We have just two kinds of concave. We have concave up, which is like a cup, and concave down, which is like a frown. So concave up is like a cup, concave down is like a frown. Okay? We're going to be talking today about how to tell how a graph curves. We now know how to tell when it's going up and down from the first derivative, but how do you know, does it curve in a steeping up way or is it curving in a sloping this way? How do you know? The second derivative is what tells us, okay? So we're going to talk about how to tell what kind of concavity a graph has using the second derivative, and how to talk about when a graph is concave up here, concave down on the other side. What do you call that point in between? We're going to talk about that as well. So we're going to look at a parent function that you're familiar with, and that parent function is x to the third. So let's write down y equals x to the third. You remember what that graph looks like? It's a wiggle. Y'all, those of you who took pre-AP pre-calc, cross wiggle tan, this is a wiggle. So it goes up, looks like it's going to turn around, but nope, decides to keep going. What trig function looks like that? What trig function? Tangent does. Okay? So that graph definitely curves. We're going to talk about how to tell. All right? What is the derivative of x to the third? 3x squared. Okay? Now, 3x squared, no matter what I plug in for x, the sign of the first derivative will always be what? Positive. It'll always be positive, but it could be also 0, because if I plug in 0, it's going to be 0. So, if the first derivative is positive, that means that the function is what? Increasing. Isn't this graph increasing all the time? Except for maybe at 0, when it kind of stops for a split second. This graph is increasing all the time. But the question is, how do you know that it's not a straight line? Or how do you know it does this kind of curvy wiggle thing and then this shape on the other side? Well, because your teacher in Algebra 2 told you it did, right? But there is a way to tell from the equation, even if you don't have the graph and a curve. So, this means right here that it's increasing. But how do we know which way the graph curves? How do we know which way the graph curves? The answer is the second derivative tells us. Okay, so let's talk about the second derivative algebraically and then compare it to the way the picture looks. So I'm going to come down here and I want to take the second derivative of this equation right here. What is the derivative of 3x squared? 6x. Now, do you see that this one curves down at first and then it curves up on the other side? Since it doesn't curve at all pretty much in the middle, that happens to be where the derivative, the second derivative, equals 0. We'll talk a little bit more about that in a minute. So when you're trying to find the curvature of a graph or the concavity of a graph, you need to set the second derivative equal to 0. So what value do we get for x? We get 0, okay? Now, this point right here has a name. The point where the graph changes concavity is called a point of inflection. And it is a point where F changes concavity. Now I could tell from the graph that it does. I'm going to algebraically prove to you that it does as well. Now I've kind of got ahead of myself a little bit, but that's okay. Take a look at this derivative again. Does this derivative ever fail? No. Okay. It doesn't fail because there is no denominator in there for x. So f double prime must equal 0 or fail at a POI. POI is the widely accepted abbreviation for point of inflection. Okay. After you find where the derivative equals 0 and then where it fails, we're actually going to make a number line like we did for the first derivative. So I'm going to make my number line up here. And this is an f double prime number line. I'm going to put my 0 on it. And I'm going to be using quite a few colors today. So I want to pick a number to the left of 0 to plug into the second derivative. What should I plug in? -1. Let's try -1. Now remember, we're plugging into the second derivative. What sign will it be when I plug -1 into the second derivative? It'll be -6, which means it's negative. Agreed? If I plug in +1 to the second derivative, that will be positive. Agreed? Okay. So, do you notice that it changed sign right here? That is where it changes concavity as well. Okay? Now, let's talk about what this means about f prime. On the graphs that we've done before, is this procedure that we're doing similar to what you've been doing on the other worksheet? Except we've been working with the first derivative. Now we're working with the second derivative. Before, this said f prime and this said f. Now this is saying f double prime and this is saying the one below that, f prime. If f double prime is negative, then f prime is decreasing. And if f double prime is positive, then f prime is increasing. Now, f prime decreasing and increasing is kind of a strange thing to say. What I'm talking about is this. I'm going to take this purple piece of paper and I'm going to put it over here. As you go up this curve, are the slopes of the tangent lines represented by the purple paper getting bigger or smaller? They're getting smaller, aren't they? The slope down here is like -3. The slope right here is about -1, maybe -1/2, and so on. When I say the slopes are getting smaller, that's the derivative decreasing. Does that make sense? Derivative decreasing means the slopes are getting smaller. So I'm just going to put an arrow here, slopes getting smaller. I know I'm writing kind of small. The slopes are getting smaller. And that's very important because that's what's happening to the curvature. Now on the other side it says f prime is increasing, which means the slopes are getting bigger. Look at it. The slope right here is like 0, and then it's getting steeper and steeper and steeper as you go up. Does that make sense? So here the slopes are getting bigger. Okay. So when f double prime is negative, f prime is decreasing. And what does that tell us about f? What I told you before class started, that piece of graph right there, does that look like a concave down piece or a concave up piece? That looks like half of a concave down piece, right? Concave down is like a frown. So this means the graph is concave down. When f double prime is negative, F prime is decreasing, and F is concave down. And when F double prime is positive, looking at this other side, that piece of graph is concave up, is it not? Do you see it? It's half of a cup. So this means concave up. So this is concave down, and this is concave up. So this is concave down, and I'm abbreviating here, and this is concave up. Now, some of you are going to have some difficulty seeing the concavity. It helps if you just take a piece of paper and cover up the half of the graph you're looking at. That piece of graph right there, doesn't that look like half of an upside down parabola? Yes. Doesn't that right there look like half of a right side up parabola? That's how you can tell the concavity. Okay. So, the point where F changes concavity, did it not? According to my symbols, at 0, it changed from concave down to concave up. Therefore, 0 is a point of inflection. So, point of inflection, if you want to write this down, is right there. Point of inflection is a point where the graph changes concavity. Any questions up to this point? All right, let's summarize what we've just talked about here. And this is what I want you to leave class understanding today, right here. Point number 1. If F double prime is negative, that leads to F prime is decreasing, and that leads to F is concave down. Those three are tied together. When F double prime is negative, F prime is decreasing, and that means F is concave down. Are we good on that one? Point number 2, when F double prime is positive, that means that F prime is increasing, and that means that F is concave up. F double prime is positive, means that F prime is increasing, and that means that F is concave up. What we just wrote down here is exactly what this chart is. Let me kind of walk you through it. F double prime is negative, F prime is decreasing, F is concave down, and then F double prime is positive, F prime is increasing, and F is concave up. Do we have any questions at this point? Okay, what I'm going to do now is we're going to do a problem. You have no idea what the graph looks like, and we're going to talk about where it's concave up and down, and we're going to find its points of inflection as well. All right? Any questions before I move on? I'm going to go to a new sheet of paper, just because I don't think I'm going to fit the whole thing right there. That's just me. Everybody done with this page? All right. So, here's our example. Can you see? Yes. F of x equals 1/10 x to the 5th minus 1/2 x to the 4th plus 10x minus 7. 1/10 x to the 5th minus 1/2 x to the 4th plus 10x minus 7. The directions say find where F is concave up and down and locate points of inflection. Find where F is concave up and down and locate points of inflection. Okay, I believe that you guys can take the derivative of this twice, but correctly. So, when you read a problem, look for the keywords to work with. This one says the phrase concave up and down. It also says the phrase points of inflection. Both of those refer to the second derivative. Okay? So, because it says both of these, you have to work with the second derivative. If it had said increasing and decreasing, which derivative would you work with? First derivative. Okay? But because it says concavity and it says points of inflection, I'm working with second. So, I would like you with your table to take the second derivative of this function and then check it with your neighbor and make sure you got the same answer. Okay, look up here and see if you got what I got once you checked with your table. Okay. When we set the first derivative equal to 0, what are we looking for? Who remembers? The worksheet that you're turning in tomorrow. What are you finding when you set the first derivative equal to 0? Maxes and mins. When we set the second derivative equal to 0, we are finding possible points of inflection. Okay? So, what we need to do now is we need to set this equal to 0. And I'm going to write down to find potential POIs, potential points of inflection. Just because it equals 0 does not necessarily mean it's going to be a point of inflection. For the same reason that just because the first derivative equals 0 doesn't necessarily mean it's going to be a max or min. It's a potential. Okay? How do I solve that? Do the thingy. That doesn't help me. Factor out what? 2x squared. Very good. Okay? That leaves me with x minus 3. Then we set each one equal to 0. What does x equal in the first problem? 2x squared equals 0. X equals what? 0. And x equals... Okay. Those are our potential points of inflection. Okay? Derivative equals 0. And the second derivative fails. Yes or no? Okay, talk to your table and tell each other why the derivative does or does not fail. Because I'm going to call on a table in a minute to tell me. This is the one concept that I think a lot of students still struggle with. Okay? Table 1. Does the derivative fail, yes or no, and why? No, because it does not have a... What? Okay. The answer is denominator. Okay. Can you be a little more specific? What doesn't have a denominator?
X. There's no X.
There's no x in the denominator of f double prime. F double prime, because that's the one we're checking for failure. Okay, so no. No failure. Very good. Okay, so now we move on to the number line. We label it f double prime. We put on the number line 0 and 3. Okay. We are going to do this by hand. Okay? Very carefully. We are plugging into f double prime because this is an f double prime number line. Pick a number smaller than 0, please. Negative 1. I'm plugging into the factored derivative. Okay? When I plug negative 1 into 2x squared, what sign will it be? It'll be positive because I'm squaring it. So that's a positive times a negative 1 minus 3 is a negative. So that's negative right there. Pick a number between 0 and 3, please. 1. Plugging 1 into 2x squared is a positive. Plugging 1 into x minus 3 is a negative. Oh, it's negative again. That's okay. Now, pick a number bigger than 3. 4. Plugging 4 into 2x squared would be positive. Plugging 4 into the parentheses would be positive again. So the whole thing is positive. Okay. Now, this is telling me what f double prime is. Now, let's talk about what f prime is. If f double prime is negative, f prime is decreasing. If f double prime is negative, it's decreasing again. F double prime is positive, f prime is increasing. Okay? Now we go to the last step, which is f. When f double prime is negative, f prime is decreasing. F is what?
Concave down.
Concave down. So draw a little concave down like that. Next one, concave down again. Concave up. Okay? Are we good on that? Okay. According to the tip inflection, the graph must change concavity at that point. Does the graph change concavity at 0?
No.
No. Therefore, 0, even though it came out to be one of the points where it equals 0, is not a point of inflection. So I marked it out. It's not a POI. Does the graph change concavity at 3? Yes. So my point of inflection is at 3, comma something. Which equation do I plug it into to find what goes with 3? The original. Plug into F to get it, and I'll tell you what the answer is because I don't want to take the time. It's 6.8. So the point of inflection is at 3, 6.8. That's where it changes concavity. Okay, so let's go back to the question. It says find where F is concave up and down. I did, but that's not enough of an answer. A sign chart is not considered an answer in calculus. You have to write it out. And find the points of inflection. I already did the second part. Now I got to do the first part. So concave up, dot, dot, concave down, dot, dot. I needed an interval notation. Okay, what is the interval where it is concave up? From where to where? 3 to infinity. Okay. Now, I've got 2 concave downs that are right next to each other. Many people ask, can I just write negative infinity all the way up to 3? The answer is no, because it's not concave down at 0. So what we have to do is 2 separate ones. So it'd be negative infinity up to 0, and then 0 up to 3. And this right here is my answer. It's what it asked for. It asked for where it's concave up and down and where the points of inflection are. Okay. Any questions on these problems? Yes, ma'am. I think I did it in the calculator. Did you do it in the calculator and get a different answer? Yeah. No, I did it in the calculator. Yeah. Okay. Another question. Anybody? Okay. Let's do a quick little mini quiz to wrap this up. Okay. Listen carefully to the question. Talk to your table about the procedure that you would do to find points of inflection on a function. Ready, go. How do you find points of inflection? What do you do? Okay. Table 3. I need a volunteer to tell me what the procedure is to find a point of inflection. Who wants to volunteer? Okay. Okay, what would happen if they were points of inflection? How would you know? Like up there on the one that we did, one was not. Jimena, tell me, how do you know?
The signs would change.
The signs of what would change?
F double prime.
Thank you. Very good. If the signs of f double prime change, it's going to be a point of inflection. Does that make sense? Okay. So, you take the second derivative, you set it equal to 0. You don't take the first derivative and set it equal to 0, you take the second derivative and set it equal to 0. That's the big thing you've got to remember. Because it's so easy to confuse maxes and mins with points of inflection. And you do the wrong derivative. I cannot tell you how many years I've taught this and how many years every time kids get those confused. Okay. Now the next question is everybody listen, fill in the blank. F is concave down when f double prime is blank. Negative. Very good. F is concave down when f double prime is negative. Okay, listen carefully. F is concave up when f prime is what? Increasing. Very good. Okay. Here's the next question. F has a point of inflection when f double prime changes from negative to positive. Okay, this is a formula quiz question. It would say f has a point of inflection when f double prime change or blank. You could say changes from positive to negative, but you got to put or vice versa because it can go the other way. But the quickest way to say it changes what? Sign. That's even faster. It changes sign. Now, extension question. F has a point of inflection when f prime changes what?
Slope. Or signs of the slope.
Increasing to decreasing or vice versa, but there's one word that describes that whole thing.
Direction.
Direction. When f prime changes direction, aren't these arrows changing direction? Yes. F has a point of inflection when f prime changes direction. Okay, are you following me? And f double prime changes sign. All right. Very good. All right.